Okay, so here's a Zoom meeting for Physics 232C. So we have an exam this week. This is Monday. We have an exam Thursday. Chapter 18 is the chapter we're studying now, and the homework problems for chapter 18 are due Wednesday, and then the exam is Thursday. So remember to make a help sheet that you can refer to during the exam. One sheet of paper, two-sided, handwritten, for the chapters 15, 16, 17, 18. Now, you probably already read chapter 18. A lot of people have already done the reading quiz. Anyway, you should read chapter 18 and take notes. So, for example, these are some of the equations that you should have in your notebook. The magnetic field is defined by the force that it exerts on a charged particle. If a charged particle with charge Q is traveling with a velocity v through a magnetic field, then the force that acts on Q is Q v cross B. That's called the Lorentz force. So it has a direction perpendicular to both V and B. V and B defines a plane. Perpendicular to that plane is the direction of the force. The magnitude of the force is QVB times the sine of the angle between V and B. So unlike the electric force, which just depends on a charge, the magnetic force depends on the charge times the velocity, which is sort of like the current. So it's a current-dependent force. The magnetic force on a current in a wire is given by dividing up the wire into small lengths dl, many small lengths dl, and then replace Q times V by I times dl. They have the same units. This is charge meters per second. This is charge per second times meters. So these would have the same units. There's a section on applications of magnetic forces. Many of the applications that are listed in the book are for charged particles moving on a circle. If a charged particle moves in a constant magnetic field, it moves on a circle. Or more generally, it's circular in the plane perpendicular to the magnetic field, and then linear in the direction of the magnetic field. So in most general motion of a charged particle in a magnetic field is a helix. But anyway, if it's planar, then it's a circle. And you can use the equations from physics 231. The mass times the acceleration is equal to the centripetal force. Well, the centripetal force will be QVB. Centripetal acceleration is V squared over R. So you have this equation which relates R and V. And there are many applications listed. We'll see some examples in a minute. Now, where do magnetic fields come from? Well, they come from magnets. That's the most common example of a magnetic field. But more generally, or more fundamentally, they're produced by electric currents. So, for example, if you have a current I in a long straight wire, then the magnetic field curls around the wire. It has magnitude mu naught I over 2 pi r, where mu naught is a universal constant. And then the direction is around the wire. Or if you have a circular coil a coil of circular loops of wire carrying current I, then the magnetic field at the center of that coil of wire is mu naught Ni over 2r, r is the radius of the circle, times the direction k hat, which is the axis of the circle. So here are two examples of magnetic fields produced by electric currents. Now, what about the magnetic field produced by a magnet? Of course, not very many materials can be magnetized. There are only 3 elements that can be magnetized: iron, nickel, and cobalt. The most familiar example of a magnet is magnetized iron, piece of iron. Where's the current? There's no obvious current if you just have a bar magnet, a piece of magnetized iron. Where's the current? Well, the current is in the atoms. So all the atoms have an associated circular motion of charge for the case of iron, nickel, and cobalt. And those magnetic fields of the individual atoms will all add up to make a macroscopic magnetic field. So really, the origin of magnetism is electric current. It's just that the most familiar kind of magnet is a piece of magnetized iron, and that's there the current is not so obvious because it's inside. Well, it's belongs to the atom. The individual atom is too small to see. All right, well, anyway, these equations you should have written down in your notebook when you took notes. And these are the equations. They're not complete. There's some of the equations we'll need for the next assignment, which is due Wednesday, and for the exam, which is Thursday. Of course, magnets are extremely important in everyday life. For example, an electric motor has a magnet. Electric motors produce rotational motion. The torque that causes that rotational motion is caused by a magnetic field acting on a loop of wire. So here's a kind of a generic, or they call it schematic diagram of an electric motor. It's got a magnetic field, and it's got a loop of wire which carries current. So you have some sort of current source, maybe a battery, creating the current in this coil, and the magnetic field could be produced by permanent magnets, more likely by electromagnets. And there'll be a torque on the coil, and so you'll produce rotational motion. And that rotational, all motors have rotational motion. Now, here's the question. An electric motor makes use of torque on a current loop in a magnetic field to do work. Suppose a washing machine motor has a square coil, 100 turns of wire carrying current I in a magnetic field B. What's the torque? Well, the torque depends on the orientation of the wire or of the loop. So the torque will be strongest when the loop is in the plane of the magnetic field. That is to say, where the plane of the loop is parallel to the magnetic field. And so we're going to calculate that torque. That's when the torque is a maximum. So in all physics problems, the first thing we do is draw a picture. We already have a picture, but this picture is not much good for our purposes, so we'll draw our own picture. Here's the coil of wire. It's got a current in this direction. Here's the positive side, here's the positive terminal of the battery. So there'll be a current going around this coil of wire from the positive terminal back to the negative terminal. So what would that be? That would be clockwise, I guess. So here's a clockwise current. Here's the magnetic field in the plane of the coil. Now the Lorentz force is I dl cross B. So you have to use the right-hand rule to figure out the direction of the force. Here, I is to the left, B is pointing out towards you. So I cross B, I guess I have this backwards. I cross B would be in the other direction. By the right-hand rule, if my fingers point in the direction of I, and my thumb curls around to the direction of B, then I cross B points actually upward. So I've got this backwards. So this should be in the other direction. And over here, I points to the right, B points out towards you. If I use the right-hand rule and consider I cross B, the force will be downward. So you see you have a force in one direction on one side, a force in the other direction on the other side, and that's going to be a torque. There's no net force because the force over here exactly cancels the force over here. So the total force on the torque on the coil is zero. But the force is separated. On one side it's in one direction, on the other side it's in the other direction, opposite to what I drew here. But anyway, that makes a torque. So there'll be a torque, which is what we're supposed to calculate. So here's the picture, try to get it right. Label it. There's a width here and a length. Now the torque, remember from physics 231, the torque is R cross F. It's R, the distance from the axis to the force, and then the distance, and then times the force. So the distance from the axis is going to be like this. Here's the axis. So the distance to the axis, from the axis to the force, will in both cases be W over 2. So you have W over 2, there'll be two equal forces in opposite directions, so times F. And then I have to multiply by 2 because there are two contributions to the torque. This side contributes a force in one direction. This corresponds to a force in the other direction. So the two torques will be in the same direction, so they add. So I multiply by 2. Now what's the force? Well, the force is ILB sine theta, but in this case, sine of theta is 1 because theta is 90 degrees. Theta is the direction between the electric field, the electric current, and the magnetic field. Well, at this point, where the coil is parallel to the magnetic field, that direction is 90 degrees. Sine of 90 degrees is 1. So the force will be ILB. That would be for one turn of wire, but there are N 100 turns of wire. So I have to multiply by N to get the total force on this side of the coil and the same force on this side of the coil, but in the opposite directions from what I had drawn. All right, so now we've drawn a picture, we've written the equations, we have to apply a little bit of algebra and do a calculation. The torque is going to be W over 2. Now W in this case is no, it's going to be WF. WF, the twos cancel. So WF, F will be ILBN. So W is 8 centimeters. I is 5.2 amps. L is also 8 centimeters. B is 0.55 Tesla. And have to multiply by the number of turns of wire, so 100. So as usual, we have a calculation to do here. The answer will be a number with a unit. Now the number you can calculate with your calculator, but you can't calculate the unit with your calculator. You have to look at the expression to see what the unit is. It's going to be centimeters times centimeters. I could convert that into meters, and then I would have meters squared, amps, and Tesla. So the unit here will be Tesla meters squared per amp. Now 8 times 8 is 64, but remember I have to convert this to meters, so I should multiply by 0.01 to convert from meters to centimeters. So I have 64 times 0.0001. That's the product of these two terms. And then 5.2, well, I'm going to take more or less half of that. So let's just say it's about a half. We can approximate this by 0.5. So this will be a half of 5, be about 2.5, maybe closer to 2.6. There's another factor of 100 in here. So now you just multiply these numbers together. You get something like 1.5. The 10 to the minus 4 here and the 10 to the 2 here gives me 10 to the minus 2, and this is another 10 to the minus 2. So the powers of 10 will all cancel out, and I'll end up with 1.5. And as for the unit, a Tesla is a volt second per meter squared. So Tesla meter squared is volt seconds. So it'll be volt seconds divided by amps. Amps is coulombs per second. Let's see. Tesla is volt seconds per meter squared. So that'll be volt seconds divided by amps. Oh, divided by amps. Oh, divided by, I don't know if I've got the power of, don't seem to have the right unit here for some reason. Well, the seconds doesn't make sense to me, but here's the volt. Amp is coulombs per second. So this seems to be volt per coulomb. Yeah, volt per coulomb would be joules. That's the same as Newton meters. So I'm not sure where I went wrong here in the units, but anyway, the unit should be the unit of torque, which is force times distance. And I should look a little more carefully about the units. Tesla is the unit of B, and that's volts. That's the unit of, so the unit of B is Tesla, and B has the same units as E divided by C. So that's volt per meter divided by meters per second. That's volt seconds per meter squared. I'm confused here. Why? Oh, no, the amps are in the numerator. No, there's a mistake here. This should be Tesla meter squared times amps. So I calculated this unit wrong. Yeah, so this is volts per coulomb because the amps should be in the numerator. And amps is coulombs per second. So I've got a little mistake here. You can always check your units because I know it has to be Newton meters is torque. And volt is coulomb times joules. So I have here joules has the same units as Newton meters. So anyway, that's what goes in here. This is only approximate, but you can do it more accurately with a calculator. Should be 1.5, close to that, Newton meters. All right, so that's an example of the magnetic force acting on an electric current. Here's another problem from the homework assignment for Wednesday. An electron is moving in the y direction with some speed v, I guess that's given, through a magnetic field which is in the minus x direction. What's the force on the electron? And what's the electric field that would make the net force 0? So there are two parts to this question. And our first step should be to draw a picture. So here's a picture. Let's draw X, Y, and Z axes. So X and Y are this plane, Z is perpendicular to the plane. The velocity is in the Y direction. So here's the electron and its velocity is in the Y direction. So its velocity is this way. There's a magnetic field in the minus X direction. So here's the magnetic field in the negative X direction. Now the force will be the charge times V cross B. Now V cross B you get from the right-hand rule. So V is this direction. So that's V. B is in this direction. So that's B. Now use the right-hand rule to get V cross B. Let the fingers of your right hand point in the direction of V and then curl in the direction of B. Then your thumb will point in the direction of V cross B. So this is V cross B. And now the force will be the electric charge, which is negative times V cross B. So if I take this direction and multiply by a negative number, the force will be in the opposite direction. So the force will be in the minus Z direction, pointing downward. So here's the force pointing downward. That's the picture. Now we need the equations. Well, we're going to deal with the force. So the force is negative E V cross B. Now, V and B are here perpendicular. So the magnitude of V cross B will just be VB sine of 90 degrees because the direction is the directions are 90 degrees apart. So the magnitude of the force will just be EVB. Take the magnitude, this sign doesn't matter. So by the right-hand rule, the direction is vertically downward, the magnitude is EVB. Now, what am I supposed to calculate here? First of all, what's the direction? Well, I can see the direction is in the negative Z direction. So it has an X component, which is 0. It has a Y component, which is 0. It has a Z component, which is negative 1. That gives me the unit vector in the direction of the force. Namely, it's in the negative Z direction. 0, 0, minus 1. And now what's the electric field? I keep doing that. What's the electric field? Well, UX is 0, so EX will be 0. UY is 0, so EY will be 0. UZ is -1, so EZ will be -1 times EVB. Keeps going wrong here. Oh no, sorry. Here's the force. The force will just be EVB. That's the magnitude of the force. So the magnitude of the force will be EVB. Okay, so that takes care of part A. Now part B is, what would be the electric field that would cancel that magnetic force? So in other words, if we also had an electric field, if there was also an electric field here, the electron would feel 0 force as it goes through here, because the magnetic force would just cancel the electric force. Now we need a force in the opposite direction, so it'll cancel. So that means E has to be in the negative Z direction, so that the force is in the positive Z direction, force on a negative charge. So EX would be 0, EY would be 0, EZ would be in the negative direction, so it'd be a negative direction. Well, you know, minus EV cross B minus EE, that would be the net force. So this is the net force on the electron. That has to be 0. And then the electron will just pass through that volume of space with no deflection, because the net force is 0. Okay. Any questions? Let me look on the chat box. I don't see any questions on the chat box. Anybody want to type a question in the chat box, or just unmute your microphone and speak up? Okay, well, here's another problem. In 1897, the English physicist J.J. Thomson used crossed electric and magnetic fields to measure the charge to mass ratio of electrons. In that previous problem, in part B, we considered crossed fields, B in one direction, E in the other direction. Now, J.J. Thomson's apparatus is sort of sketched here. It had cathode and an anode to accelerate the cathode rays. Cathode rays are just electrons. A cathode ray is just a stream of electrons. And the cathode, the electrons would be repelled from the cathode, attracted to the anode, so they would come out with some velocity. Then they pass through an electric field from these two plates. So there would be an electric field and also a magnetic field. Here's a north magnetic pole and a south magnetic pole. So there'll also be a magnetic field here. The magnetic field that points from the north pole to the south pole. Now, as the electron passes through a magnetic field, it moves on a circle. So, you know, V is to the right, B is back into the page. So by the right-hand rule, V cross B will be pointing out towards me. No, B is back into the page. So V cross B, let's see, V is to the right. B is back into the page. B, I guess I have that backwards then. V cross B would be up. So an electron would be pushed down. Well, this shows the electron being pushed up. So I guess this drawing is wrong. This must be the South Pole. This must be the North Pole. But anyway, the electron, as it goes through the magnetic field, will be deflected by that magnetic field. And by measuring the deflection, J.J. Thomson could determine the ratio E divided by the ratio of the charge divided by the mass. Now, of course, the charge of an electron is negative E, and the mass is known. The mass of the electron is known. So in this way, Thomson could use an apparatus like this to measure E divided by M. He made the assumption that the cathode ray is just a stream of identical particles. A stream of particles, all with the same charge, all with the same mass. And sure enough, he found that all the cathode ray was deflected in the same direction. And then he would observe that on this deflection scale. All right, so now part A is just to calculate E over M. Well, you can look up E in the book. You can look up M in the book. So you can just calculate E over M, looking up the charge of an electron and the mass of an electron. So that's done. Part B is, what's the charge to mass ratio of a proton? Protons are a little more difficult to produce. I mean, electrons you can produce by heating up a metal and applying an electric field. So this would be the experiment of Thomson. Just out of curiosity, what's the charge to mass ratio of a proton? The charge is the same, but the mass is much bigger for a proton. So the charge to mass ratio will be much smaller for a proton. That takes care of part B. So far we haven't had to do any work. Just look up the constants and calculate the ratio. But now part C is a calculation. It says in one experiment, electrons were accelerated to a speed v by the electric field, namely this electric field, and then deflected by a magnetic field, namely this magnetic field, in a magnetic field B. B was known. So what would the circular arc, what would be the radius of the arc of this arc of a circle? You know, while it's in the magnetic field, it's traveling on a circle. But then once it comes out of the magnetic field, it's traveling in free space, so it's just a straight line. So what's the radius of that circular arc inside the magnetic field? Well, I should draw a picture really, but here are the equations. First of all, we need to know the speed. Well, the electron was accelerated in this electric field, so 1/2 mv squared, final kinetic energy, would be the amount of potential energy that it picks up by going through the potential difference, delta V, times its charge, which is E. So 1/2 mv squared will be E times delta V. And delta V, you know from chapter 16, is the electric field times delta X, the distance that it was accelerated. So this is just conservation of energy. This is the potential energy. No, this is the work done by the electric field. That'll be equal to the kinetic energy that it has when it leaves the electric field. So there's one equation. Now, what do we know? We know the electric field, so that's known. We know the distance in the electric field, so that's known. We know the magnetic field. Well, okay. So, and of course, we know the electric charge and the mass, because those are just constants of an electron. So from this equation, we can calculate V. Then for the circular arc, where it's deflected, we have charged particle on a circular arc. mv squared over r is EVB. So now we know EVB, we know R, we know M. So now we can calculate R. So that's the answer to part C, this radius R. By the way, you notice that in this equation, it doesn't depend on M and E separately. It only depends on the ratio, E divided by M. And in this equation, it doesn't depend on E and M separately. It only depends on the ratio, E divided by M. So the result here, R, will be determined by the ratio, E divided by M. So Thomson was not able to determine E separately, nor M separately. All he could determine was E divided by M. This was the experiment where electrons were discovered. The fact that all the particles in the stream of the cathode ray are deflected by the same amount just proves that they all have the same value of E divided by M. And Thomson made the assumption that these are all the same particle. You know, they're all electrons. It was an American physicist, actually, who first measured E. And that was Millikan in the Millikan oil drop experiment. That was an experiment where it was possible to measure E by itself. And so Thomson measured E over M, Millikan measured E, that determines what M is. And that led to a lot of this early knowledge of atoms. So anyway, to calculate R, we just, use algebra here, multiply both sides of the equation by R, divide by EVB. So R is MV divided by EB. So that's M over E, V over B. Now we figured out V from this equation, and we're given B, given the value of B. So we can calculate what would be R. And again, you're going to have a number with a unit. Well, if you check the units, the unit will come out to be meters. Now here's a question on the chat box. Not a question about the current problem solved, but it's not a question about the current problem, sorry. But is there a way to take the exam earlier than 7 p.m. Thursday, since it is online? No. But if you can't take the exam at 7 p.m., then you need to send an email and request the makeup exam, take the exam the next day. The exam will be open from 7 to 10 p.m. So it'll open at 7 p.m. It'll close at 10 p.m. and you have 70 minutes, a 70-minute stretch of time to do the exam between 7 and 10 p.m. But if you need to do the makeup exam again instead, then read the FAQ about makeup exams. Here's another question. Do you have any other resource recommendations? Okay, so let me come back to that in a minute. And one more problem to consider. I think this is the last one. Yeah. Okay, in 1913, J.J. Thomson discovered that atoms of the same element may have different masses. Those are called isotopes. He used a mass spectrograph, which again is just a beam of particles in electric and magnetic fields to measure the radii of circular orbits of charged ions moving in a magnetic field. So here's the picture of two different isotopes moving in a magnetic field. So the magnetic field vectors are indicated by little points here, which describe vectors pointing out towards you. So for a vector pointing towards you, we indicate that by a little dot. And the circular motion will be different for different masses. So we'll consider two isotopes with the same charge but different masses. So consider two isotopes of tin, tin 116, tin 118. They enter the magnetic field with the same kinetic energy. What's the fractional difference in radii? So that's the problem. Well, again, it's circular motion of a charged particle in a magnetic field. So the basic equation is Newton's second law. The mass times the acceleration is the force. Mass is the mass of the isotope. Acceleration is v squared over r. That's the centripetal acceleration for circular motion. And the force is EVB. So you can calculate R1 and R2 for the two different isotopes. The radius of this circle would be R1. The radius of this circle will be R2. So this distance, I guess, would be the diameter 2R2 minus the diameter 2R1. So it would be 2 times R2 minus R1. So measuring this distance gives R2 minus R1. Now the fractional difference is R2 minus R1 divided by R1. It's the difference divided by the smaller one gives you the fractional difference. All right, now somebody asked a question on the chat box. Do you have any other resource recommendations for studying for the exam? I don't feel well prepared for this exam with the textbook alone, as I'm more of a video person and homework hasn't been the best so far. Also, when are TA office hours? You have to look in the syllabus to find out when the help room is open. There's a help room in the biomedical and physical sciences building. It's on the first floor of the BPS building. Biomedical and physical sciences, room 1248. The TAs have scheduled periods in that room, and you have to look up when they're available in the syllabus. How to study for the exam. Really, the best way to study for the exam, since after all, there's no break between the final homework set and the exam day. The best preparation for the exam is to study your notes. You've been taking notes as you're reading the chapters, study those notes and convert those notes that you took in your notebook into a help sheet. 1 page, 2-sided, handwritten, mainly equations, the equations from the different, maybe a few pictures, but mainly equations. Making up that help sheet will be a good activity for studying for the exam. Another resource is at the end of every chapter, there's 1 page called the summary. So for each chapter, look at the summary. If there's something in the summary you don't recognize or you don't you don't have written down on your help sheet, go back and look at it earlier in the chapter and make sure that you understand what's on the summary. That'll give you a quick overview of each chapter. But really, the best thing to study for the exam is to study your notes. Just like if this were a lecture course, the best thing to study for an exam and a lecture course are your lecture notes. All right, so any other questions about any of these homework problems or any other homework problems? Let's you'll have equations like this written down in your notebook. Well, kind of condense them down into one page front and back for 4 chapters, so, chapters 15, 16, 17, 18. And it's already 10 minutes before 8. So we've used we've used over 45 minutes. So that's about the right length of time for these Zoom meetings. So unless there are any last minute questions, well, first of all, let me stop the recording.